In this lecture, we look at graphs of functions focusing on finding intercepts. An x-intercept is a place where the graph touches the x-axis, that is, where y is equal to 0. A y-intercept is a place where the graph of our function intercepts the y-axis, so x is 0. If we're given an equation for a function f of x, it is easy to determine the y-intercept. We simply compute f of 0. It can in general be harder to find the x-intercepts of the function since we're seeking to solve the equation y equals 0 or f of x equals 0 for x values. Here are some examples of how we might approach this problem. Let's find the intercepts of the following functions. Problem number 1, f of x is a quadratic, x squared minus 2x minus 3. In the second problem, g of x is a rational function, 1 over x plus 2 plus 2x minus 3 over 2x plus 1 plus x minus 5. To do problem 1, we notice that this has y-intercepts 0 minus 3 because the y-intercept is where x is 0. Plug in x equals 0, we get out minus 3. But to find the x-intercepts of this function, we need to solve the equation 0 is x squared minus 2x minus 3. The x-intercept is where y is 0, so we wrote out 0 equals x squared minus 2x minus 3. This is a quadratic, and we can factor the quadratic into x minus 3 times x plus 1 and solve 0 is equal to x minus 3x plus 1. The product of two expressions is 0 if and only if one of the expressions is 0. So either 0 is x minus 3, the expression on the left, or 0 is x plus 1, the factor on the right. Thus the x-intercepts occur where x is 3 or x is minus 1. So the x-intercepts are the points minus 1 comma 0 and 3 comma 0. Let's look at the second function, this rational function. The y-intercepts of the function g of x equals this expression occur where x is 0. So if you want the y-intercept, we replace x with 0, do the computation, work it out, and eventually we get minus 15 halves. So the y-intercept is 0 comma minus 15 halves. The x-intercept is where y equals 0. So we examine the equation 0 equals this expression. This is going to be a little more complicated. Our goal is to solve for x. To do that, we multiply both sides by the denominators, x plus 2 and 2x plus 1, to clear denominators. In general, we want to get rid of denominators. I don't like denominators. If we do that, we get 0 is equal to 2x plus 1, that's what the first fraction becomes, x plus 2 times 2x minus 3, that's what happened to the second fraction, and then finally x plus 2 times 2x plus 1 times x minus 5. We can expand this out and simplify. So I've expanded out the various terms, the quadratic and the cubic, collect like terms, and I get this cubic. 0 is 2x cubed minus 3x squared minus 20x minus 15. In this course in general, we will not work out the generic solutions to a cubic equation, but in this case, when we have this cubic, we can do some trial and error or use a graphing calculator and discover that x equals minus 1 is one of the solutions to this equation. If we know that, we can then factor the cubic into x plus 1 times this quadratic. We'll do a lot of this in part 2 of our course. To solve the equation, 0 equals 2x squared minus 5x minus 15, that quadratic, we need the quadratic formula, and so after we plug in a equals 2, b equals minus 5, and c equals minus 15 into the classic quadratic formula and simplify, our solutions are 1/4 times 5 plus or minus 3 square root of 5. So the x-intercepts, after a bit of hard work, are minus 1, 0, 5 plus 3 root 5 over 4, comma 0, and 5 minus 3 root 5 over 4, comma 0. We'll look more at this problem later. In the definition of function, we require that a function have a unique output for each input. The geometric version of this requirement is called the vertical line test. The points in the plane corresponding to a fixed x value form a vertical line. For example, the line x equals 3 is simply a vertical line consisting of all points of the form 3 comma y for any value of y. If we graph a function, then each vertical line must touch the graph at exactly one point, at the y value where y is equal to f of x. So to see if our graph is the graph of a function, we can draw vertical lines and see if these lines intercept the graph exactly once. For example, in the image below, we have a graph drawn in red and a vertical line in yellow corresponding to a particular x value. In this case, it's the x value x equals 0. Notice that this vertical line hits the curve exactly once in the place where x is 0 and y is f of 0. This should be true for all the elements in the domain of the function. Any x value we plug in should give us a vertical line that hits the graph in exactly one point. A variety of applications in science require that we understand where a function is rising or falling, and that we be able to find the local minimums and local maximums of a function. We will want to know where the x values for which f of x is as large as possible in some particular region, or where f of x is as small as possible. Later, in calculus, we will find a universal approach to this very important problem. But at this stage, we're content to draw graphs and find minimums and maximums visually. For example, consider this fourth degree polynomial, f of x equals x to the fourth minus 8x squared, with the graph drawn below. Where is this function increasing? Where is it decreasing? What are the low points on the curve, the local minimums? What are the high points on the curve, the local maximums? We can see that the function drops from the left to the point where x is minus 2 and y is minus 16, and then it rises back up to the origin, and then it drops again down to 2 minus 16, and then rises after that. So the function is decreasing for x values in the region from minus infinity to minus 2, in other words, to the left of minus 2. It's also decreasing between 0 and 2, but it's rising in the region from minus 2 to 0, and then to the right of 2. The local minimums occur when x is minus 2 and so the y value is minus 16, or when x is positive 2 and the y value is minus 16. The local maximums occur at the single point 0, 0, at the origin. In the next lesson, we will look at piecewise functions.